Ladies and gentlemen, from the Institute of Natural Mathematical Science, Richard Yulo. His presentation is The Evolution of Spherical Bacteria and the Fight Against Antibiotic-Resistance. Welcome, Richard.
Bacteria come in different shapes, but many of them evolved to become spherical. Most of these spherical bacteria are harmless, but some do cause serious infections, such as gonorrhea and pneumonia. Some of them have even become resistant to our strongest antibiotics, becoming superbugs that kill about 1 million people every year. The problem is, we don't really have a very good understanding of how these spherical bacteria work, making it that much more difficult to fight them. So, the goal of my research is to learn more about what makes these bacteria tick in order to develop new strategies for fighting antibiotic resistance. As it turns out, all bacteria evolved from an ancestor that had a rod-like shape. Maintaining this shape is important because the way bacteria reproduce relies heavily on them growing this way. In fact, in experiments where rod-shaped bacteria are given a drug that made them spherical, the cells just kept getting bigger and bigger until they burst. How then did spherical bacteria that exist today become successful? To answer this, we took some rod-shaped bacteria and deleted an important gene, making them spherical. As expected, these cells just kept getting bigger and bigger. They were very weak and easily killed. But what's important is that although they were very sick, some of them survived. So we took those survivors and allowed them to grow and reproduce for 1,000 generations, letting evolution take over. At the end of the experiment, they became healthy again. Somehow they found a way to adapt to this sudden change in shape. Naturally, we were interested in how they did this, so we studied their DNA and we found mutations that changed the way they were building their cell walls. Interestingly, these same mutations also made them resistant to antibiotics used in hospitals today. It seems that as bacteria go through this transition from being rod-like to spherical, they end up strengthening their cell walls, making themselves resistant to our collection of antibiotics. So, now that we know what these bacteria are changing within them to make themselves stronger, we can potentially use this information against them by designing new drugs that specifically target those mechanisms. We're still filling in the gaps, but hopefully what we learn from this will give us the upper hand in our fight against antibiotic resistance. Thank you.
Thank you, Richard.
Fascinating research, Richard, and you explained it incredibly clearly for the non-scientists among us who could follow sort of exactly what you did and what you're hoping to achieve through that. So really well done. I think the method and the clarity in that explanation and where it's all going, it was just perfectly explained.
Thank you, Richard. I really like the way in which you start off at a very micro level and then you pan out and take us into the application. And on that little journey in 3 minutes, we've understood something about the structure of these entities and something about evolution. I'm still thinking about 1,000 generations. How does that happen? And then, you know, the resilience and the strength and the particular characteristics that are embedded along the way. So great story, great narrative and great application. Thank you.
Indeed. Congratulations, Richard.